Thanks everyone for coming to a talk with such a scary title. Personally, monad transformers scared me for years until they finally clicked, so I'm happy to say that I'm finally comfortable with them and they help me solve real problems in real life. So, no, there is hope. I'm Clément. I work at a company called Fretlink, where I'm a developer. I mainly use Haskell and PureScript in my day-to-day job. And previously, I was the CTO at a cloud company where I used Scala a lot. And now I've switched to more principal languages. But Scala is still a nice language. I talk a lot of shit on Twitter. So if you have questions or remarks and everything, don't hesitate to send me tweets, and then we can discuss it afterwards. Quickly, I'm working at Fretlink. It's a freight company, a logistics company, and we help shippers ship things, and we help them work with small carriers. So we work with big shippers like Procter & Gamble, and we make them work with really small carriers. And it's cool. Legacy code, or legacy, historical monolith is Node plus Mongo, and all new services are written in Haskell and PostgreSQL. And the front is using React and PureScript, which is quite an interesting technical stack and an enjoyable technical stack to work with. So today I will try to debunk the common saying FP in the small, OP in the large. Think it comes from F# mainly. And I will try to show how we can do FP in the small and FP in the large as well. And there's this idea that FP is good for interesting code, really business logic, stuff like that. And that boring architecture infrastructure code is better off as imperative and with imperative languages and with OOP for modularization. And to me, I would say FP is good for absolutely everything, but maybe I'm biased. And we always talk about interesting algorithm and stuff like that, and we always neglect the plumbing. And today, I will talk about plumbing. So, in the context of web services, that's what I'm authoring the most, so that's how I think mainly. We try to have the simple code and clean code inside a hexagon, and then all the mess is outside, or at least we try to. In FP, it's quite a natural way to do it. We don't have to come up with names to do it. We just put the I/O at the edge of the system. For a typical HTTP request-response lifecycle, what we usually do is that we start by parsing the HTTP request. Then, based on that information, we do some routing. Usually, it will then involve reading stuff from a database, then the pure, nice, mighty business logic, which is perfect, and then back to the trenches, writing stuff in the database, serializing stuff to HTTP, choosing an HTTP code, and so on. Of course, to that, we have to add calling external services, and in production system, we like to observe things, so maybe writing logs, maybe sending messages to Sentry because we hit an unexpected code path. And in Haskell, the runtime has a really good story about observability. You can have counters, gauges, stuff like that. Remember distributions. And you can do all that, and usually it's not in the business logic. It will be in the dirty layers. The business logic will return pure values, and then you act on them effectively in the outer layers. Of course, business logic is a solved problem, so I won't talk about it. We all know how to do it quickly and cleanly. cleanly, so no problem. Today I will focus on these outer layers that are usually left to imperative programming and show that there are solutions in purely functional code to handle them in a way that's modular and quite satisfying. I will show one way, there are others, but the way I will show is commonly used and it's quite effective. So in Haskell, for instance, it's really natural to push I/O to the edge of the system. There is no fancy name for that. It's just something you naturally do. And we naturally do it because I/O shows up in types in Haskell. You can do I/O without having it show up in the types. And this small pane, it nudges you into pushing I/O to the outside of the system. This way your models stay pure, and then the I/O is neatly pushed at the edge of the system. And it's just natural to do that because it's a path of least resistance. Let's see how it happens practically. Let's say I want to read the host name of my machine from the environment. So there is a function called getEnv, which will read an environment variable for me. And you can see in the type, so the things are after the 2 colons at the top, it will not return a string. It will return an I/O action that will give me a string. Or not, maybe it can crash if the environment variable is not defined. So you can't do I/O and not having it show up in the types. And let's say I want now to display it. I can execute my I/O action to read the environment, get my string, and then display it. There is special syntax for this in Haskell. It's called the do block. And you can see that there is a small leftwards arrow and not a regular equal sign. Because get host, its type, it's not a string. So the arrow, in a way, it unpacks the I/O to give me the string. And in this block, host, the host variable is a string and not an I/O action. So the do block, it allows me to put I/O actions one after the other. And of course, in imperative languages, the order of the line matters because implicitly, one line is executed after another. In Haskell, which is pure, it has no statements, only expressions. So if we want to have one line executed after the other, we have to explicitly say it, for instance, with a do block. You can do the same thing in Scala, but in Scala, it's not provided by the type system directly. You have to use a library to do that, so it's opt-in. For these examples, I've used a library called cats.io. And the regular print line and getEnv operations I can do in Scala don't show the I/O in the type, so I have to wrap them myself. But once I've done that, like in Haskell, instead of a do block, it's called a for comprehension, but it's the same thing essentially. It sequences the effects. Then it reads from environment, and after that, it writes on the standard output. And since it's in Scala, I have to manually go from I/O to regular type. Hopefully, this function, I call it only once in my system in the main entry point. And all the rest of my program is using explicit I/O types. So, having one action is good, but I want to combine them. As we've seen, we can combine I/O action with do blocks. And I've said it's a specific syntax, but it's just syntactic sugar. What it actually desugars to is function calls. So in this code, it's really the same as the previous slide. I run my, I have my I/O action that reads the host from the environment, and then I give it a callback, which will be called with the value returned by my I/O action. So if I've been able to read the environment variable, then it will call my function, providing the string as an argument, and then it will put the value on standard output. So this function has this type. So in Haskell, 2 colons mean has type. And what I really like in Haskell is that we don't mix types with values. So we have the type, and then we have the implementation. So here we can focus on what this function does. We call it bind, and what does bind do? It takes an I/O action that will return an A, and it works for any A. So lowercase types in Haskell are parametric types. And then it takes a function that turns this A into a new action, and then it returns the result of these actions. So the intuition here is that it has to be sequenced. You can't have the second I/O action if you don't have the first value, because you wouldn't be able to call this function and get this value. So that's what it means. In Scala, it's the same. Instead of bind, we have a function called flatMap, but it's essentially the same. And if you're more comfortable with Scala types, it says for all A and B, I forgot the B, flatMap allows me to turn an I/O of A using a function from A to I/O of B to I/O of B. And we can do that with I/O, and it's usually the first place you see it, because when you program, you usually end up doing I/O. But it's not only with I/O. In here, I just don't do I/O. I also have to handle errors for HTTP layer, saying either I can return a projection of my resource, or I can return an error explaining what went wrong. That is something I can handle like this as well, and providing stuff like connection pools or clients for observability systems and so on. And this is a thing we call effect, as opposed to the side effect, which is something the code does but does not show up explicitly. An effect is something the code does, but it shows up explicitly. And an effect is always, you can always see it as a type that's parametric on another type. And it says, yes, you will get this value of type A, but it will be in a context. It's not just the value. It's maybe the context that I've done some I/O, I've performed some I/O to get this value. So in Haskell, you will always have a type that's parametric on an A, and in Scala, it's the same. For instance, where in Java we have checked exceptions, in Haskell, we can do it with a regular data type. It's called either, and what it means is that either I have a value of type E, or I have a value of type A. So by convention, and for very good reason, E represents the error, and A represents the actual value we want. And when we fix the error type, then we're back to a type with only one type parameter, and this is an effect. An effect saying, maybe you'll get this value, or maybe you'll get an error instead, a bit like checked exceptions. And continuing with checked exceptions, you can combine them. In code that can throw exception, each line is executed only if no one before has thrown an exception. In Haskell with either is the same. I have either an E or an A, and then I can use the value that I got in the first step to turn it into maybe or into either an error of a value of type B. And in the end, I get either an error of a value or a value of type B. And you can see that the function, I can't call it if the first effect resulted in an error. So if there is an error at the first step, I will just return the error and be done with it. On the contrary, if I get a real value, then I will be able to call my function and then continue on. In Scala, it's a bit more verbose, but it's essentially the same. Now let's talk dependency injection. It's a super important, and in the OOP world, it's a driving force, really. The main framework in Java is built, or the two main frameworks, assuming JE is not dead yet, but the two main frameworks, they are built around dependency injection. And in Java, it's complex. You have containers, runtime reflection, stuff like that. It's really, really complex. In Haskell, DI is kind of simple. DI, essentially, it means I can do something, but to do it, I need another thing. And that's just a function. DI is just functions. You need it, well, you put it as a parameter to your function and be done with it. And if somebody wants to call this function, then they will have to provide the dependencies you need. And that's all. And that's essentially how we do it in Haskell. Let's say we have a cat and it needs a cheeseburger to nap, or whatever cats do, maybe scratch your arms or hide on a sofa, I don't know. You can model it as a function and it will work. If you have the dependencies and you call the function, you provide it with dependencies, and then you have your result. What we usually do is that we don't work with functions directly. We wrap it in something called a new type. It's just a wrapper, and it's unwrapped during compilation, so it's essentially free at runtime. And instead of having a function, we say, I can provide an app if we give me a cheeseburger. And then you put the function in it. But usually with dependencies, it's something deep down that needs a dependency, and then all the way back up, you don't need the dependency anymore. You just have to thread down the dependency. So using directly function would be tedious because you would have to copy the dependencies. A bit like in React when you're copying props down your tree, and it's tedious, and instead you use context and you hide it. It's a bit like this, unless we're not in JavaScript, so we do it thing explicitly. DI, we can combine it with the same function as well. If I can provide you an A with some dependency E, then I can call a function and have my result. So actually, it looks like that. I can chain my operations, and then the resulting operation will carry out the dependencies. I don't have to thread manually the dependencies. So we've seen that, we've seen that, we've seen that. Maybe you can notice a pattern between these three functions. I hope so. And this is the same function, the same signature, essentially, because it's the same object. And this object, we call it monads, because yeah, got have to find names. And it's that. For all M can be, you can think of it as an effect. If I have an M of A and a function from A to M of B, then I get my M of B. And really, what you need to understand here is that it's sequential composition. You can't call the function if you have not worked on the first value, because if you want to call the function, then you have to get an A. And that's the essence of monads. It's not burritos or spacesuits or anything. It's just there in this function. You need to call things one after the other. Monads have a few more operations. What we will use, it's pure. It takes a value and puts it in the context that does nothing. And this, it shows that all these operators are really about lifting a function into a different system. But it's not really that important for what we'll see today. And please remember that monads come with laws that code uses. So if you implement your own monads, you got to make sure that you follow these laws. But as users, tooling will tell you when you can apply this law to reduce your code. And monads are really useful in plumbing, because in plumbing, it's always about composing things sequentially. And the composition itself, it's not about the values. Usually, there is no deep logic for the values we pass down during the plumbing. What is important is that all the context, the DI, saying we do effects, handling errors, that's the important thing. And that's where monads are really useful, because they describe sequential composition, and it comes up everywhere. So what we've seen is that it's kind of easy to combine effectful value or monadic values. But in a system, we don't have only one effect. We don't have only I/O or just DI or just observability. We have all of them together. So what we really want to be is to be able to compose effects. And that would mean compose monads. And sadly, monads don't compose in general. So you can't take two monads, put them together, one in the other, and then have this behave as a monad. You can try to implement it to get the feeling of why it can't be done. Try to do it by yourself as an exercise and not end up trying to do it in real code, not realizing you're trying to compose monads and it will never work. I've lost a few afternoons to that. I don't really recommend it. But there is a good news. Some monads will compose with all monads, and that's what monad transformers are. Let's say I have any monad M. If I wrap a maybe value, so an option, in this monad, then I can get back monadic composition. Same with either. I wrap my either into any monad, and this combination forms a monad. And I can do that with DI, or we call it reader in Haskell and Scala. Please note that the M is not at the outside, but in the inside, and it's a really interesting thing you can think about. If you want to brush up your parametricity, stuff like that, it's really interesting, but I won't go in details. And all these monads, they can turn any monad into a new monad that are transformed or augmented. It takes an effect, any effect, and it augments it with a specific new effect. It takes any monad, and it adds the ability to throw errors. It takes any monad and adds the ability to have access to DI. So by convention, we put the monad and we put a T at the end, and that is a monad transformer. And then we can say how it behaves like a monad. And what it actually looks like in code is that lookup env, it does not give me an IO of string. It will give me an IO of maybe string. So if the env variable is not there, it won't crash. It will just tell me that that's not there. So if I want to compose those two values, I wrap them into a maybe T to tell the compiler how to compose them, and then I can compose them as I want. And last step, I remove the transformer to just expose an IO of maybe string and not bother callers with this implementation detail. Scala, as always, it's the same with much more ceremony, but it's the same. And it looks like this. I wrap my nested monads into a transformer, and then I'm able to compose them. So we've seen how to compose two effects, but remember that when you compose, when you put a transformer and you give it one monad, it gives you another monad. So you can put it in another transformer, and that's a stack. It's called a stack because the outermost monad, mostly I/O, it's at the bottom of the stack, and you add up effects on top of it. That's why we call it a stack. And then you can compose all the effects you want, and get a big value, and then it does everything you need. For instance, in a web framework, I can have a type handler, which says, yeah, you can do I/O, but you can also return HTTP errors if you can't get the resource you need. And this gives me a stack, and I can augment this stack with DI, saying, OK, I can do I/O, I can throw errors, but I can also read context to do things. And the code looks like this. I can compose it with a do block. It says, given a user ID, I will generate a transaction to get my user from DB, run this transaction. Then I get a result. And if the result actually carries a user, then I'm done. And if not, I can return a 404 error. The actual way to write throw error is not that simple when you think of it, because composition and pure, it carries all the context in one step. When you want to throw an error, you are talking about one specific layer of your monad stack. And that's a bit more complex. But we'll see how to not worry about it. And it's Scala again. It's the same with more parentheses and square brackets. I can compose things. And this handles DI, error, and I/O. Everything just has to return the handler with conf type. And I'm golden. It's good, and it works, and it has been really satisfying for many people, but there is still something that bothers me with this approach. There is a saying that tells us we should program to an interface, not to an implementation. And putting the actual monad stack everywhere in the types, it's essentially programming to an implementation. And what we want to do is to program to an interface instead. Thankfully, there is a solution. You can make things declarative, saying, I need this effect, and that's all. You don't have to say, I want this effect, and this other one, because outside in the code it's used, and it's in this particular order. That would be tedious. There is a thing called transformer classes. You can think of them as interfaces, and they describe the intent, the behavior of your transformer, without committing to a specific type. What it looks like is that, hey, I want to read configuration. OK, there is a function ask, which tells me that I can read the environment. And it will be in a context, any context, as long as it can give me access to the environment. If I want to throw errors, same. I can throw an error, and it will give me a value in a context, any context. I just need to know that this context, that the actual context that will get executed, can handle errors, and that's all. And same for I/O. And this way, we can rewrite our code in a more agnostic manner. Let's say our DB library, it provides us with a function. You give it a transaction, a connection pool, and it does some I/O, and then it returns a value from the database. I can wrap it into another function that says, yeah, for any monad M, I don't really care which one. I just need to be able to read the config, where I can get my DB pool, and I just need to do some I/O, and that's all. And then in the code, you say, yeah, let's give me the DB pool that's stored in our config type, and then run some I/O, and lift I/O turns an I/O into any monad that can do I/O. So in this code, we turn something that was really prescriptive into something really declarative. We just list the capabilities we want and the effects we will do, and that's all. And you can see that I don't do any error handling, because error handling is for the HTTP layer. And here, I don't do HTTP. I just do I/O and DI. Of course, in the actual handler, I will need to handle HTTP. So its type will be a bit bigger. It will say, For any monad M, I want to do I/O. I want to have access to the config. And then I may throw errors if I'm not happy. Of course, it's a big type, so we can hide it into a type alias. And that's what we usually do. For one project, we just say what every handler will do, and we put it in a type. And then I have a function that turns my user ID into a user in a context. Any context, I just know that this context will be able to handle DI, I/O, and error management. And then the code is the same as before. I create my transaction, I run it against the DB, and then I pattern match on my results and maybe throw an error. And here's the throw error. It's the function provided by the interface monad error. And it will work with any monad that can handle errors. So my business code, it's just interfaces and no more implementation. And when you want to actually do things, because at the end of the day you want to do things, providers, you can use transformers. You create your monad stack, and you will have an implementation already available. It's for free because you don't have to implement it yourself. It's not really for free because when you have a monad stack, there is function delegation to know which function to call and how to rewrap everything. So there is a perf hit, but my advice is that as long as you don't have perf issues and with proper measurements, then don't try to optimize upfront. And if by chance you really have a performance problem, you can switch to a more performant implementation because all your code is independent of the interpreter. You can have a single data type and implement all these functions by hand, and you won't have all the wrapping taking place, and it will be more performant. Of course, it's cool. And that's the style we use in my company for all web services. We have a layer for HTTP errors, I/O, DI, a layer for observability, and a layer for access control. So I can say this value is available as long as the user proves that they can do that. And that's cool. You can stay tied to transformers, but you can go further. Instead of staying tied to transformers, saying I will throw an error or I want DI, which is really tied to the actual transformers, you can actually describe your business logic in those constraints. It's a style called tagless final, and you create interfaces saying what you will do. In terms of hexagonal architecture, it's kind of like a port. I'm no expert in hexagonal architecture, but it really looks like a port to me. And instead of saying, I will do I/O stuff, you will say, I have an effect, and it will be able to fetch some users for me. I don't care the actual implementation. I just care I want to be able to do that. And with that, you can mock things. You can have an interpreter for production that is efficient, an interpreter for development that logs more things. You can do what you want because you've separated implementation from intent. And you can do that in functional programming as well. The only thing you still have to do if you use transformer is to design your stack. And it's a bit more complex than what you might think. When you describe effects in your business logic, you just say effects, and there is no order in it. But when you provide an actual interpreter, then you have to think a bit harder at what you put in it. And the most common error is to try to turn every monad you come into a layer in your stack. And your interpreter will be the same for all your system. So it only has to carry the common effects. If you have more effects, then you can have them explicitly in functions, because it's not about being free from implementation for all your system. It's this function. It has the specific things it needs to do, and you have to be explicit about it. Because with all the transformer classes, you can add things, but you can't eliminate it. So as soon as you've put monad error in your effects, then every endpoint will carry the effect that it can have error. And that you can't go back from that. So if you, at some point, want to return an error, but you know it will be handled afterwards, and you have to remove it from the effects, then you can't put it in the stack, and you have to model it explicitly. But the good thing is that for users, for consumers, people who write the domain logic, they don't have to care about it. It's only an implementation detail at the end of the world. So not everyone in the team has to think about it. And in our company, we are a few people caring about it, but the rest of the team, they just happily describe effects, and they're OK with that. So this style with classes, it's called MTL. It's really powerful. It works really well if the framework you're using is based on transformers, and it's good. There is a performance hit. I won't deny it, but don't try to chase performance just for the sake of performance. It's common advice, but don't be scared by this performance hit. You can still use transformer in your business logic just because you want to combine things, but it's not a driving force for the design of your whole application. And there are two uses that are not incompatible. And don't panic. I know this is quite advanced, and it can be scary. I was scared by it before. But it works, and it's a pragmatic solution that really works. In my team, there are people who are Haskell beginners, and they work with this style, and they don't have any issue with it. Because the complexity is just separated at one hand of the code, and not everybody has to touch it. And also, try to consider how it's done in your favorite framework. And would you be able to talk about it and describe it during 1 hour, going from nothing in Spring or JE? I'm not sure. So, of course, it looks complicated, but there's nothing big in it, and you can compose it by yourself. The kind of things that I do in Haskell Web Frameworks, I don't know how I could do that in Java on Scala. And I'm not sure it's even possible to do that. So please focus on the ergonomics of the user and accept the small complexity cost that's needed for interpreters. I promise you it's worth it. If you want to read more, there is an article called Refactoring to a Monad Transformer Stack in a really small CLI tool. So it's easier to follow, less concerns, fewer effects. There is a good article if you want. If you're OK with monad transformers and want to understand MTL better, there is an article called MTL is not a monad transformer library, which is really good and really well written. And yeah, that's all. We're still hiring, and we don't hire Haskell programmers that already know everything. We hire people that we are happy to work with, and then we do in-house training. We have 5 minutes for questions, so go ahead if you want. Yeah?
So if I wanted to have logging in my business logic, I would have to make all of the, basically the business logic type declarations would have to have the monad type.
OK, so the question was about putting logging in business logic. What I would do personally is not put the effects down there, but surface the logging, the values, as part of the result. And then I get the logging, and then I can send it to the logging system. But I get the chance to do more things, maybe augment it with the context of the request and everything. There are ways you can just return a tuple with the value and maybe a list of lines. There is a thing called the writer monad that does that for you. But what I would do is return a pure value with the logging and then send off the logging to the logging systems effectfully. Yeah. There was another question in the back.
Yeah, thank you for your presentation. It
Thanks.
was very interesting. As a disclaimer, I'm not a Haskell advanced programmer, but there is also, I would like to ask if you heard about this extensible effect library for Haskell, that it's an alternative to monad transformers, and what do you think about that?
Okay. So the monad transformers to compose effects, it uses complex theory and everything, but in the end, it's just a pragmatic choice. It's not seen as a clean solution at all in the Haskell community. And the clean solution is something called the extensible effects. You have that in PureScript, or you had that in PureScript, for instance, and there are libraries in Scala and Haskell. It's also something that's explored. No silver bullet yet. I have not worked with them personally. Some people are really happy with them. I'm happy with MTL and monad transformers. For instance, in OCaml, it's the way they've decided to go. Monad transformer are like a dirty solution, but they work reasonably well. So they're still really used in Haskell because they solve a problem with not too much issues. But it's not the only solution. And it's definitely not the one that's deemed the solution. Extensible effect would be the solution, but there are still usability and performance issues.
Other question?
Okay. Thanks, everyone.